Okay, what we're going to be going through here is just a basic example on how you tackle a problem here for linear regression analysis. Now, I have to alert you that I've done this video previously here and listed it under regression analysis, but because it's related to managerial cost accounting really, and specifically cost analysis or cost behavior, I'm going to list it as such here. But it's a good problem to go through here to look at the different tests that we have to do here when we're using linear regression analysis. So we'll continue on with the problem. What we're going to be going over here is where we're going to be evaluating an estimated cost function, and we've used linear regression analysis here to estimate this cost function. Okay, so this is what we're talking about, and we'll start out with an XY coordinate plot here. And I've really got 12 different data points here shown by those little red squares here. And each one of those data points has an XY coordinate. So the X coordinate for each data point is on our X-axis, and that's represented as machine hours, which we refer to as our cost driver here. And that is our independent variable here. And then the Y coordinate, that is along our Y-axis, and that represents the indirect manufacturing labor cost here. And that's our dependent variable. So what we're trying to do here is we're trying to predict our indirect manufacturing labor cost or dollars here based on some linear regression here based on machine hours here. Okay, so what I've done here, I've got a linear regression line shown with this green line, with this upward sloping green line here, and I've used the least squares method here, a statistical method, to estimate that line here. And those 12 different data points that we're talking about here, just showing them, our X data points are here, our Y data points here. Y is the indirect manufacturing labor cost that we have for our 12 different data points. X here is the machine hours here. And then based on the equation that I've estimated with the linear regression here, least squares method, we come up with the Y, or the predicted indirect manufacturing labor cost here. Okay, so what we're going to try to do is we're going to try to evaluate how well this line here, based on machine hours, fits our data here, and how well we can predict our indirect manufacturing labor cost here based on machine hours. And just to understand what this line is here, if I calculated it out here with a statistical package here, used Excel here, and it's got 10.3 here. That's really the slope of the line. That's how much it increases here. And what we're saying by the slope here, for every machine hour here, it goes up $10.3 dollars here in direct manufacturing labor costs. So for every machine hour, we have $10.3 dollars here in indirect manufacturing labor cost. Plus, we have what they call a y-intercept here. We have to add 300 here. So 300 is where we have X machine hours, we still have Y indirect labor cost here of $300. So that's the equation, the simple linear equation here that we're going to be analyzing here to see how accurate this, we can, with this linear, based on our 12 different data points, how accurate based on machine hours, the linear regression, how accurate we can predict our indirect manufacturing labor cost here. Okay, so let's go over here, and these are really two different tests we're going to look at here. First, we're going to have the R squared test. That's really a correlation test between our X independent variable that we have here, the machine hours, and our Y dependent variable. That's the indirect manufacturing labor cost that we're trying to predict. And we use an F test to do that, and we'll go into that here. Okay, so that's our R squared. That's the good, might be referred to as the goodness of fit test here. Then our second test is really regression analysis here, and that's where we're looking at the significance of the independent variable. In this case, the independent variable is machine hours, which are trying to, based on what we're trying to predict indirect manufacturing labor cost front. So the regression analysis is really where we're trying to look at a significant relationship between our X independent variable and our Y dependent variable. So we're going to be testing the slope here, this line, that Y equals M, slope of the line, times X, in this case the machine hours, plus B, the y-intercept here. And we're going to be using linear regression using what they call the t-test here. And we're looking at a 5% significance level or a 95% confidence level. And really we're going to be analyzing this data, and it's going to be based on some Excel output here where we use the data analysis and the regression function here in our data analysis. And it would be similar for any other statistical software. Okay, so maybe let's just go understand what we're talking about. If you're not familiar with the regression here under Excel, you select the data analysis pack here, hit regression, and it's going to come up here where you're going to have a regression just to understand the inputs. So you really got two different inputs in this case. The input Y range here, and that would be our indirect labor here. I'm showing that here. That would be the B column here, B column 2 through 13 here. And then the input X range, that is our machine hours here, and that you'd put in column A here, row 2 through 13. We have those 12 different data points. You put that in, and then there's a few other selections you can make for other items that you want to be looking at here under regression analysis. Hit enter, and you're going to get what we're going to be looking at next. You're going to get some Excel output in this case. And it would be similar for any other statistical package. But just so you understand, your Y input range here, that would be what you have as your dependent variable. In this case, it's our B column for indirect labor. And our X input range here, that is the independent variable. In this case, it's machine hours. And we're trying to use those machine hours here to correct our indirect labor. And that's how we got our linear regression line here. Okay, so next let's just go and look at the output that we've which was given to us based on the regression analysis here and what we had put in as our machine hours and our indirect labor hours. Okay, now for analyzing our data, now remember X equals our machine hours and Y represents our indirect labor dollars here, predicted by X, our machine hours here. So we're going to start with our regression statistics here, and we'll look at our R squared and our standard error here. Now, those represent the correlation or the goodness of fit. Now, the R squared here, that's also referred to as the coefficient of determination. And really, that's the proportion of the variation in Y, the dependent variable, that's explained here by X, the independent variable. Okay, so let's get a pictorial or understand what each of these are. So we'll start with our standard error here. Now going back to our XY coordinate plot here, really we have two different lines that we're looking at here. We're going to have this little blue line, that's our Y, or that's our mean average line for all our Y values here. And then we have our regression line, that green line that's sloping up, that fits those data points here. Now, we have those 12 different data points. So really what the standard error is, in this case it's 170. And it gives you an idea of what the variance is on each side of that fitted regression line here. How much your data varies here, and it's 170 in this case here. Gives you an idea what the spread is. But the other items that are really critical here to get understanding what they are, we have the total sums of squares, TSS here, and that's really the difference between each of those Y values here and the average mean Y value here. That squared distance for each of them, it's all summed up here. And then we have the residual sums of squares. In the blue was total sums of squares is shown as this blue line here, but the residual sums of squares, that's that green line of this green arrows here, and that's really the difference between each of the Y actual values and what the predicted value would be here on your regression line. All right, so that's the residual sums of squares, and then the explained sums of squares that's shown in gold here. That's the difference between your Y mean value and the actual predicted value here for each of your Y values. Okay, so what you're attempting to do here with this R squared here, really the equation is 1 minus the fraction here. You're looking at your residual sums of squared divided by your total sums of squared. That gives you your R squared, or it could be equal to your explained sums of squares, the ratio here of your explained sums of squares, the gold here, divided by your total sums of squares here. So that's what we're talking about, R squared. And really, if you look at the relationships here, your total sums of squares here, the blue, equals your explained sums of squares here, plus your residual sums of squares, just to get an idea what they are here. Okay, so let's go up and now let's look at our R-squared value here. It's at 0.52 or 52%. So this is what we're going to have to check for. They're saying that anything above 30% gives you some correlation here of goodness of fit. 52% is probably a moderate fit here. And again, we had our standard error here. So what we have to do is we have to test for our R-squared here. And we use the, over here, we use the F test for this correlation here. So this is based on an F distribution. And what we have to do is we have to determine a critical value. In this case, we're using a 5% significance level. And we're going to come up and we have to calculate that critical level, a critical number. And I'm using Excel here, and it's really, the equation is here, the function is equals f dot inv dot rt, and then you have to put in your significance level. In this case, it's the percentage. It could be 5% here, but you have two different degrees of freedom that you're going to put in. You can take that right off the Excel table here, but we're going to have to go and understand what those degrees of freedom are. So first off, just for our equation here, the regression, that's the ESS here. We have 1 degree of freedom that Excel is printing out, and then the other one is for the residual RSS here. We have 10 degrees of freedom here. Put that in, hit your enter, and you're going to get a critical value of 4.964 here. And that's what we're going to use in our F distribution here. But before we get into that, let's go and let's understand those degrees of freedom here, because you have to know what those, if you're not given this here and you're working with some software package, you have to come up with and understand what your degrees of freedom are in order to get that critical value here. Okay, so let's go and look at that here. Okay, so here it is. To determine your degrees of freedom here, and what we're going to be looking at here is really that regression equation here, y equals mx plus b. K is the number of different coefficients that we're talking about. So K, if we had, in our case, we only have one coefficient here, one slope m here. But if you had an equation where you had 3 different predictors, x1, x2, and x3, and you had 3 different slopes here, beta 1, beta 2, and beta 3, you'd have 3 degrees of freedom here that you'd be looking at for your K value here. And then n is just the number of observations. In this case, we have 12 here. But if we go back to our equation here, just understand what they are here. The TSS that we talked about, it's that let's just look at it up here. That TSS, the total sums of squares, it's 1 n number of data observations or data points minus 1 here. And then the ESS, that's our regression sums of squares here. To explain sums of squares, that's just equal to K. That's the number of coefficients in our equation that we have here. And then RSS here. So RSS is just taking n, total data points or observations, and subtract from it the quantity here, K plus 1 here. So in this case, if you had K at 3, or 3, you'd have 3 plus 1. In our case, it's only 1. We only have 1 coefficient, so K plus 1 here. Subtract that from n, 12 data points, and we should come up with 10 here. Sure enough. So there with our RSS, we have 10. You can see the TSS here, 11, n minus 1 that we looked at. And ESS, that was just the explain sums of squares. That's just the number of coefficients we have in our equation. Number of slopes, or m predictors here. Okay, so put that in, and we would have come up with our critical value that we can put in our F distribution plot here. That's an F curve, essentially, is what we're talking about. And this is at the 5% critical level, at 4.96 we come up with. So what we're going to be looking at is testing the F value. So let's understand what that F value is here. Really, that F value in this case, we have a 10.89 here. And that's really taking really explain sums of squares here, taking the mean squares. That's the average value, number of data points divided by the total sums or the sums of squares for each of those here. So we have explain sums of squares, ESS, the mean square of that, divided by RSS, that's mean square here, divided out here. And that's going to give you F, your degrees of freedom. In this case, it's 10.89. And then we also have what we have a significance F test, and that's really whatever this F number is here, it gives you a percentage as far as that. In this case, we were looking at that 5% critical value here. This 0.008 is really 0.8 0.8%. So we're pretty good here with the significance. So we passed that already here. But to understand that significance before we get into that, it's really, you go into your Excel functions again, equals f.dist.rt, and then you put in that critical value we have here at 4.96, and then those degrees of freedom 1 and 10 here. 1 for our ESS, 10 for our residuals here. And you're going to come up with just 0.5088 or 5% here. That's it. But you can see here, just going to our curve here, now if we're testing it, the F value that we have is actually 10.89 here. So our critical value was 4.96. So what we're saying is, because it ends up in the tail here, yes, we passed the test, or we have some degree of correlation here. You can get an idea of how much correlation we have here because it's greater than our critical value here, 4.96. If it was less here, then no, we wouldn't be passing our F test. If it was, say, 3, 2, or 1 or whatever here, then no, or anything less than 4.96. We're setting at 10.89, so yes, based on our F test here, our R squared correlation gives us that correlation between what our X variable here is explaining, or X independent variable is explaining the variation in Y here. And then you can see the 5% would have been sitting here. We're sitting way out here at point, we're way less here. 5% would, in anything, this is 5% and then gets lesser and lesser and lesser. And when we get at this 10.89, this is where we're talking about that 0.8%. Okay, so that's our F test. We passed our F test here. You get an idea what it is here. The next thing we have to do, let's go down here. Now we have to work with our coefficients here, or what we have, the regression here, or that independent variable that we have. We have to check the independent variable, how well that fits our equation. We got the R squared correlation. Now we're looking at what they call the regression here. So what we're going to have here in this Excel output is really we got our y-intercept value here, and then our x variable, the m here. So let's just understand that. So we got our predictors showing here, our coefficients showing here, and then we're going to have our standard error here. Then we're going to have a t-stat, a p-value, and then the confidence interval. So for our coefficients here, to understand what they are, that y-intercept here, it's come up with 300.97. That is shown in our equation here. That's that b value here. And then our x variable that we're looking at, that was the m slope, the 10.3 here. That's shown here in our equation, 10.3 times x. So that's the equation that we have here. Slope m here and coefficient or intercept b here. But when we go through these statistics, these intercept statistics, they can be wacky here. Really, you shouldn't really have to be concerned with them in this case here. What we want to be concerned with is this, our x variable, or that slope equation here that we have, the 10.31. Okay, so maybe we're going to have to come up with a t-distribution here in this case. But let's get to that. So we take our t-stat here is just taking that coefficient that we have and divide it by the standard error. In this case, it's 3.12, the standard error here on our what the computer says here. So you divide that into your coefficient, and you're going to come up with your t-stat here of 3.3 some here, and then it's got a corresponding p-value of 0.008 here. Okay, so this is where we're going to have to develop our t-distribution, and it's really a two-tailed test here with Excel here. So let's understand what that is. You can get that F distribution, excuse me, could have came off some F table here. I use the Excel function to determine your F distribution, but I'll use the same thing here using the F or Excel function to determine our t distribution, but you could use a t table as well here. But nonetheless, let's go and let's determine our t distribution here, our critical values here that we're going to be checking for. So what we want to do is go over here, and the equation is equal t here equals inv dot 2t, and then you have to put in your significance 5% here, and you have to know what your degrees of freedom are here, and you have to know what that is. So the degrees of freedom in this case, using our t distribution here, equals n, that's the number of observations, and then k minus k, the coefficient. So if we, in this case, we only had one coefficient in our equation here, so k would be equal to 1, and then you subtract 1 from it here. So what do we have here? 12 observations, 1 coefficient k here, and then subtract 1 from it. So we're going to come up with 10 here. 10 degrees of freedom. Put that into your function here, and you're going to come up with your critical value here of 2.28 here. So that's our t critical value here. So you put it on, you get this normal distribution or a t distribution here, and it's two tails. So what you want to do here, you're going to have a minus 2.28 for the critical value and a plus 0.228 here for your critical value. And the t-stat, this is what you're comparing that t-stat and essentially that probability to as well here. So your t-stat, what do we get that? That was that 3.3 here. So again, same thing here. It's greater than our 2.28, our critical value here, and that's based on that 95% here. So we're greater than that, so we passed the test. So the deal is here, if it would be less than 2.28 or in between minus 2.28 here and plus 2.28, we would fail the test. But because it's greater than 2.28 to 3.30, we passed the test. So x1, it is significant here. It's saying that that slope here has significance and we can use it here based on our t-test here, just so you understand that. And then I'm just showing the p-value of the probability again over on this side here. It would be on both, we're talking about symmetry here, or either tail here, but I'm just showing I got a room here. So our probability, our critical value would have been 5%. So had we p-value been 6, 7, 8%, we would have failed the test because it would be in this area. But 5% or less is sitting over here, and ours is actually sitting at 0.8 of a percent. So we're sitting out here. So again, we passed the test because we're sitting in these tails with our p-value here, our probability here, and also our t-stat or a t-distribution here, sitting off in the tail. So as long as we're not less than 2.228 here, or in between in this 95% range here, as long as we're not less than that, or we're sitting in this range, we pass the test. As long as we're sitting, our numbers come out and we're sitting over in these tails here. Okay, so that's our regression here for independent variable. And yes, based on our t-stat and our p-value here, our x, our m, our slope here, that 10.3 has some significance. And then the other thing is here, the confidence interval here. And really don't be concerned with the y-intercept here. In this case here, what we want to be concerned with is that x coefficient or slope here, the coefficients. And our confidence interval here is really built off that standard error that we're talking about here. It comes off that standard error here. But we're sitting with a lower level would be 3.35 here. Now remember, we got that 10.31 here. And then the upper level is sitting here at that set at 17 here. So really what you want to look for here on that confidence interval, that's based on that 95% here. And again, what you want to be looking for is to see if you got a 0 in that range here. So if we would have come up with, say we'd had a minus 3.35 here, and then there was a 0 in that range up to 17, then we would have failed the test here, because a 0, you want there, if you got a 0 in that range here, a 0 value, that is your lower bounds is less than 0 here, and of course your upper bounds would be greater than 0, so then you would have no relationship. In our case, we're sitting at 3.35 to 17.2 here, so there isn't any 0 in that range here. So because 0 does not appear in our confidence interval here, we can conclude that we have an x independent variable and a y dependent variable linear relationship. Okay, so we just went through the basics here just to understand how you'd have to go and you'd be testing after you put it into your computer software and you came up with your regression statistics. How you'd go about, you would test for your correlation, and that was your R-squared value using the F-test. And then we also looked at the significance of our independent variable, and that's what they call the regression test. To see if the t-stat here, the t-test was just used for our regression, our independent variable. In this case, we just had 1, the x here. And then our R-squared was used for our F-test or the correlation. And then, so anyway, we passed both of the tests here. Sort of a moderate value, the 52%. If we were up into 60, 70, 80%, we'd have been better off with our R squared here, but we're sitting sort of at a moderate value. But anything less than 30%, they consider a failure here. Okay, so that'll summarize our discussion. All right, just to follow up here on this p-value that we got at 0.008 here, or 0.8%. Now to determine our cutoff on this, well, it corresponds to our t-distribution here. So remember with our Excel function here, t equals our TINV2T here, where we got our t-distribution cutoff here at 2.228 here. Well, we would put that into another Excel function here, equals t dot dist.2t, and put that cutoff here, t-value cutoff at 2.28, put in your degrees of freedom of 10, and this is where you're going to get your percentage, 0.005, 005 here, so 5%. So that 5% here corresponds to the cutoff value here, t-distribution cutoff value of 2.28. Okay, so this is what you're going to do here. To determine your p-value here, you just put that 3.3 into your t-distribution function here, 10 degrees of freedom, and you should get 0.8%. Just to understand that.